Hello and welcome. In my last lecture, I discussed about photoelectric effect, the experimental details and results, and I also discussed about the laws of photoelectric emission. Now today in this lecture, I'll be discussing about why classical theory fails to explain photoelectric emission. And then I'll be discussing how photoelectric effect was explained by Einstein. Now, to discuss why classical theory fails to explain the photoelectric emission, we have to go back to the classical era of physics. The Newton, he gave corpuscular theory of light, in which he said that light is made up of particles. But later on, the wave theory of light was given by Huygens, in which he included the concept of wave fronts. This wave theory could explain the diffraction, interference, polarization of light. But there were debates going on between the scientists that is light either a particle or a wave, in spite of the fact that classical theory had an experimental proof of proving diffraction, interference, polarization, etc. When Maxwell published his theory of electromagnetic waves, then it was completely established that light is a wave because Maxwell's theory was proven correct. And these all debates and discussions, they were set at rest. But when photoelectric effect was discovered, this photoelectric effect could not be explained by the wave theory of light. The main problem with the wave theory was that the intensity of light was considered that it is actually the energy. And the intensity was proportional to the square of the amplitude. And when a light is incident on a metal, then it is electrons would absorb the energy. And these electrons would oscillate. And when the light is more intense, then more rigorous oscillation of electrons would be. And if we incident an intense beam of light on the metal, then electrons would oscillate more vigorously, and then they would come out of the surface. Therefore, we say that as the intensity increases, more energy is transferred to electrons to come out. This was against the observation and the experimental result, which we saw that maximum energy of photoelectrons is independent of intensity of incident light. Therefore, this suggestion by the wave theory was not acceptable. Again, in wave theory of light, there was a suggestion that light of any frequency, however low it is, it should be it should be capable of ejecting electrons from the surface, provided that it should be intense beam. It should have high intensity. But this again was against the established experimental result that threshold frequency, there's a threshold frequency we have seen that below which the emission of electrons is not possible. And then there was one more problem. The classical theory suggests that the emission of photoelectrons should take a long time to occur. When light is incident on the metal, then electrons would gain the energy. It will take time. And then after that, they will come out. So there's a time between the incidence of photons and the emission of electrons. But we have seen in the experiments that electrons are being emitted instantaneously when the light falls on the metal. So this was another problem which the wave theory could not explain. Then Einstein, he explained the photoelectric effect. He took an idea from Planck's radiation law, in which he said that the oscillator has a quantized energy. The oscillator has gotten energy E is equal to h nu. And although Planck, he introduced the concept of material resonators, Einstein slightly refined this concept. He said that the quanta of energy is actually associated with the photons of light. And he said that the photon of this energy, E is equal to h nu, performs two operations. One operation was that a part of this photon's energy was being absorbed by the electrons to come out of the surface. And that was known as work function, the minimum amount of energy to remove an electron from the metal surface. That was work function, the energy, how much energy is required. Then the rest of the energy was taken by the electron to gain its kinetic energy and reach the anode. Therefore, total energy of photon, this h nu was equal to the energy used in ejecting the electron, and then the rest of the energy was given to the electron as kinetic energy. And therefore, we can write down this equation, total energy of the electron, it is equal to phi 0 is work function. And this is the maximum kinetic energy the electron can gain. Or this phi 0, we have seen that this is equal to h nu 0, h nu 0. And we have also established that this maximum kinetic energy, this you can write down this as h into nu minus nu 0. And this equation is known as Einstein's photoelectric equation. And we have established that this maximum kinetic energy, it is actually the measure of the stopping potential. Stopping potential is E mu 0. E is the electronic charge. And this and 1 by 2 mv square maximum and EV, they are same. Or you can balance it, EV0 is equal to this, or V0 is equal to this equation. Now, if you plot a graph between the stopping potential, as we have plotted already, we have seen it on y-axis, and frequency on along x-axis, we will obtain a straight line. And we can compare this equation with an equation of straight line y is equal to mx plus c, where m is the slope of the line and c is the intercept on it on y-axis. Okay, and from this equation we can find the slope of the line. It is h by e, and the intercept is c is equal to h by e nu 0. And this is on y-axis. And this equation was verified by Millikan. Millikan was a Robert Millikan. He was a scientist. He was doing experiments at that time. He was unconvinced by this Einstein's photoelectric equation. He set out to prove Einstein wrong. But in the end, he proved that Einstein was right, because he conducted experiments and this equation was proved correct. And on this note, we have completed the full this topic on photoelectric effect. And in the next video, I'll be moving on next article.